Hey everyone, welcome to this next episode of Quantum Computing Podcast. In the last episode, we had just started with the first chapter, complex numbers. So we are going to continue from there in this episode. All right, so last time we had just finished this exercise 1.1.2. So what's next after that? All right, so yeah, the next paragraph is just it just covers what the complex number is, and we have already covered that. That complex number is complex number consists of real number and the imaginary number. You might remember imaginary number from last time. We had come across one imaginary number which was I, and it says that yeah, so basically a real number multiplied with imaginary number like I, the result is still imaginary number. And the formal definition introduced here is that a complex number is an expression. So if I is an imaginary number and a and b are real numbers, then a plus bi makes c complex number. Yes, and yeah, let's look at some basic arithmetic for complex numbers. So here two complex numbers are given, 3 minus I, which is given as C1, and 1 plus 4I, which is given as C2. And how would you do addition and multiplication? Addition and multiplication as well, they are straightforward. So addition, this is an example, so I'm not putting a solution, I'm just following through the solution here. So C1 plus C2 is straight forward addition. So 3 minus I plus 1 plus 4I, right here, 3 minus I plus 1 plus 4I. So 3 plus 1 is 4, minus I plus 4I minus I plus 4I is 3I. So the result is 4 plus 3I. Multiplication is also straightforward actually. It's just like not the component wise, but it's still element wise. So for an example, let's say, yeah, let's just follow through this example. This is 3 minus I multiplied by 1 plus 4I. Okay, we're just gonna use star, leave the notations and their exact meanings aside. This is just multiplication. So 3 multiplied by 1 plus 4I minus I multiplied by 1 plus 4I. So this results in 3 plus 12I minus I minus 4I square. All right, so this is 3 plus 12I minus I makes it 11I minus 4I square is minus 1. So 3 plus 11I, which is 4. So 3 plus 4, 7 plus 11I. Oh. So that's the result. And the next exercise actually is the same thing. It consists of two complex numbers. So let's calculate their sum and their multiplication. So C1 is minus 3 plus I, and then C2 is 2 minus 4I. So C1 plus C2, if you just want to do it in your head, minus 3 plus 2 is going to be minus 1, plus I minus 4I is going to be minus 3I. Okay, C1 plus C2. We'll check the answer before we move on. And C1 into C2 is going to be minus 3. Let me do it here. C1 into C2. So minus 3 into 2 minus 4i plus I into 2 minus 4i. Minus 3 into 2 minus 6. This is 12i. This is 2i. And minus 4i square. So minus 6, 12i plus 2i is 14i. And minus 4i square is minus 1. Minus 6 plus 14i. Minus 4 into minus 1 is plus 4. This is minus 6 plus 4 is minus 2 plus 14i. Let's check our results. Yeah, right here. Minus I minus 3i minus 2 plus 49. All right, so simple enough. Let's move on. So that was exercise 1.1.3. Yeah, so it also introduces the fundamental theorem of algebra. So which states that polynomial of n degree has n roots. So for an example, let's say if the polynomial equation of one variable with a complex coefficient has a complex solution. So fundamental theorem of algebra is not the starting of algebra. This is not how you start learning algebra, but it's called fundamental theorem because it really is telling you a very fundamental thing about algebra. So if it's a polynomial and if it's n degree of a polynomial with one variable is the largest exponent of that variable in that polynomial. And yeah, so if it's a polynomial with n degree, then it has n roots, and roots are just the solution of the polynomial, or whenever the value of that equation is 0. And yeah, I mean, it goes into very detail what this fundamental theorem is, but for now is good enough. Yeah, what is it? Yeah. So basically, if C is the set of complex numbers, then C is actually algebraically closed set. So the solution of the polynomial equation with complex coefficient is a complex solution which can be found within C. So you don't have to go to any other set of numbers to find the solution. So it's basically algebraically closed set. And what is next? Yeah, so yeah, here we have an opportunity to verify that minus 1 plus I is the solution of this polynomial equation. So let's do that. And when we want to verify the solution, basically we want to make sure that with this value, the value of the equation is 0. So what was it? Let's check it out. Minus 1 plus I is given, and we are x squared plus 2x plus 2 equals 0. All right, so let's say if we put x as minus 1 plus I, what happens? Minus 1 plus I square plus 2 into minus 1 plus I plus 2 equals 2, which means what? So it's minus 1 plus I minus 1 plus I plus 2 minus 1 plus I plus 2. This is the multiplication that we just learned. So minus 1 into minus 1 plus I minus 1 plus I. Yeah, let's resolve that. 2 into minus 1 is going to be minus 2 plus 2I plus 2 minus 2 and 2 are gonna go away for the next part, but we'll come back to it. So minus 1 into minus 1 is 1, minus I, this is minus I, and plus I square, this is gone, so this is 2I. So 1 minus I is 2I, plus I square is minus 1, plus 2I. 2I go away, 1 minus 1 goes away, so it's 0. Yeah, so this is true. Minus 1 plus I is the solution to this equation, polynomial equation. And just for kick, see if minus 1 minus I is also a solution or not. It is, but why is that the case? Think about it. Not important in this context, but think about it. All right, so yeah, and the next part is the programming exercise. It says that write a program that accepts two complex numbers, and the output of that program is the sum and the product. And I'll put an example. I'll put a program written in Python, very rudimentary program that I came up with. Nothing complex, I mean nothing fancy in that program on my GitHub page. And that would be the solution of programming drill. All right, so this took actually 10 minutes more than I had imagined. So we'll end here, and in the next one we will move on to the page number 10. Thank you.